Hello. Today we're going over the CAD model here of the steam engine. It's a bit of a mess here, but this is what it looks like on the inside anyway. For some reason, every time I try and hide all of these mates, they just show up these connectors. I have not figured out how to get rid of them yet, and it's really annoying, but we'll deal. But this is the engine. Let me go find my Revolute joint here. Animate. Set this to loop. Okay. Set this to transparent so we can see what's inside. So this engine is operating backwards at the moment. Oh, no, it's not. It's spinning counterclockwise. That's right. So it is spinning the right way. So as you can see here, as this slider moves, pressure comes in from the middle, pushes the top down, exhaust, pushes from the bottom, and it just repeats. This side is the intake. As you can see here, it feeds into this small tube that goes inside the valve body. The exhaust is a little bit more complicated. It feeds from the top and the bottom into this tube on the output. And then, as you can see, there are these transfer ports that go to the top and bottom of the main piston. I guess this is the advantage of using a 3D printed part, is I can make these internal channels pretty easily without having too much problems. I don't remember the exact length of all the parts off the top of my head anyway. I can go look at my spreadsheet, but that's whatever. You may notice that in the testing, this cap here was not put on. It's because when I was designing this, I didn't really think to consider how it was put together too much. And these screws just simply don't fit. I can't get the Allen key to get to them, not easily anyway. And it was causing too much friction anyway with the crank because it wasn't worn down properly and it was a mess. So. And the real one, it just isn't there, but it was supposed to be there to help keep the crank in place. As for other designs, we have this top and bottom plate for the main block here. The bottom plate has these two cone shaped pieces here and will help keep better sealing against the surfaces here. I wanted them to be separate so that they can bolt on with O-rings on the inside, but I just didn't get around to doing that. I plan on making a Mark II of this pretty soon in order to improve a lot of things, because as you may notice, there's no O-rings, gaskets, or seals. It's just running as it is. And there's a lot of friction due to the parts because I made them pretty tight tolerance, and 3D printers aren't known for their, you know, manufacturing detail. So one of these days, I either want to get an SLA printer or just redesign this and make the parts have better clearances and just use bushings, which would probably be the best for everything. It has a, I believe this is a 12 point, no, this is an 8 point spline on the output, which is connected to the flywheel right here. I actually printed two of these. The first one I made the splines a little too small and it was really hard to fit on, but the second one it fits better. It is a little warped though, if you notice in the engine running video, it wobbles a little bit. None of this is balanced. It's kind of just chucked together. It's kind of a miracle it runs. Each one of these frames is bolted from the bottom using 6 M3 screws that are countersunk. All of the screws in this build are M3 by something countersunk, except for these two bolts here, which were meant to be socket cap, but they don't fit properly, as you can clearly tell. So, don't think too much about it. Going into the more design aspects of it, this is the crank model here. It's a basic model. The valve has a 30-degree offset, I believe. Let's double check here. I believe it's 60 degrees. Well, I was wrong. But basically, since it spins counterclockwise, the valve follows just behind the piston in its stroke. So that way, whenever you're running it, the valve, as we come over here to my loop again, animate, play, loop, play again. There we go. Make this transparent again. You can see the piston or the valve body ever so slightly trails behind the main piston. This is so that way the timing can be maintained. It's a little aggressive here because I don't have a lot of space to work in here, and I kind of just made the stroke too small. So as you can tell, there's a moment here where it's just compressing the air in the cylinder with the momentum instead of getting pressure. So right now, it's pressure. Normally this would be fine with a normal steam engine because piston has quite a lot of weight. And normally you'd have 3 or 4 of these in a line, and it would help keep pressure in the system because no one piston would be in a dead spot. But since this is a single cylinder engine, it can cause it to stall quite easily. Normally the advantage with steam engines is, especially with good seals, if it gets stuck like this right here, so if I pause, stop. So if I pause, pressure will keep building inside this chamber here and keep getting dumped into the top piston. And eventually either it stalls out completely, it goes to the max boiler pressure and it just stays there, or it builds enough pressure that it starts to push the cylinder back down as it builds pressure, which basically means that they're constant torque devices, which is why they were used for so long in trains. They're incredibly powerful. Main disadvantage is just brute efficiency, especially with reciprocating engines, although that has been improved with technology. Other notes about this design. Uh, this gets really close to this surface here. I don't know if you can see how small that gap is. Let's move out of that. Move this to top of the valve stroke. It's not a lot of space. Yeah. So there's some clearance issues. These actually fit really well. The issue is on the main cylinder here, as you may notice when it's coming down, it briefly contacts the crank. Here, let's spin this the right way. So right here, there is literally no space. I don't know why I did that. It would have been easy to just cut a little bit off either one, possibly even the crank here because it's so massively oversized, but it is what it is. So that's one reason why it causes a rubbing sound every time it hits here is because it's touching. Each of these plates is solid. The block itself is mostly solid in order to keep pressure. There is a minimum of 3 millimeters of solid plastic between the inside wall and the outer wall here. That is to keep pressure. I don't remember the specific math. I could go look at it right now, but I don't care to. But it's because of that wall thickness that it can handle such pressure, even though it's made out of plastic. Because plastic is surprisingly strong if you have enough of it. The goal for one of the future designs here is to get this machined out of metal. Clearly not with this design. This design was heavily modified, so it would work well with plastic, but I'm sure it can be redesigned fairly easily. These are the connecting rods. You may notice these lips here. This has helped to minimize the contact patch of the entire rod. It also helps just maintain the bearing surfaces. You can tell that the valve one is longer and thinner, and then the crank is much thicker and more stout. That's because this is under a lot more force. This one could be way thinner here. I could have cut off a lot of material to make it lighter, but I didn't care to. I just wanted it to work. I will refine the design later. Here is the pistons. You may notice the valve is hidden here. There we go. So why does the valve look like that? Uh, because when I designed the block first, and I designed it slightly incorrectly. So all of these are a really weird space away from each other. So it would intersect with the valve here. So it would cause issues. So what I did here is that there's notches cut out on each side here. A, to maintain the pressure difference and the sealing surface, but also because the hole for the exhaust literally goes right here to the very edge, and the hole for the intake goes right here to the edge. They are not very far apart. And then the transfer ports on the inside are just barely within these two surfaces when it's in the middle. It's really weird and kind of dumb, but it does work, so I guess it's not that dumb. The reason why this one isn't as rounded as this one is because this is one solid piece. This one's two separate pieces. If I go hide the pin and the pin cap, you can see where it screws it in. This does make it horribly difficult for alignment, although it can be out of phase by about 2 degrees, I think. Still be okay. It's just, I did that because in order to install it into the block, if we come over here, you have to install it with the bottom screwed in because, you know, it has to come through here. So for the valve, because of its weird shape, I couldn't make the plate separate like I did with the main piston. So you have to insert it from the top in, unlike the main piston here, where you insert it from the bottom in and then you screw the top on. That was the wrong thing. So yeah, but this is the block here. We already looked a little bit at it earlier. You can see all of the fancy ports. These are the holes for the top and bottom threading. It's the side for the mounts. And the flanges here. Here is the mating surface for the pressure adapter I made. This fits a 1/2 inch NPT fitting, or airline fitting, I should say. And then it bolts on with two M3 socket cap bolts into the flange here. I currently don't have a gasket, but you should use silicone rubber if you actually decide to build this yourself, if you want to for some reason. I don't know why you would. This thing kind of sucks. I need to do some more work on it. This is the flywheel. I don't know why I got so fancy with designing it. It weighs 67 grams, which is just about enough to keep the engine running. It would be more than enough to keep the engine running due to its light mass and moment of inertia, if it wasn't for the fact that the friction coefficient of the entire engine is really high, even with grease, sanding, and a lot of work. So this is just barely enough. I should have made it significantly heavier, but I'm limited by plastic, so I don't know what they want from me. This is this whole thing is hilariously stupid. So this is a splined socket I made, so that way I can attach either a drill, an Allen key, or a wrench to the splines on the crankshaft in order to turn the engine over. I don't have any videos of me doing this, but I basically threw it onto a Milwaukee Gen 2 drill set to, or having the gearbox set to max speed, and just sent it for like several hours to get all the parts to interference fit with each other. It took forever, but it does run fairly smooth now. When I initially put it together, it would barely turn over even with a wrench, but now it actually turns pretty well. So it worked. Oh yeah, and about that high friction, that was after I sanded all the parts. Yeah, this thing kind of just sucked, just generally. I'll hopefully improve on version 2. If you're wondering why the design looks like this, it's because I was modeling off of, I won't grab that image because it's probably copyrighted, but I was modeling off of the engines, especially in the Titanic and other ships like the Britannica, where it's these tall engines here. Now, clearly it doesn't look the same because I can't make the part super thin or correct for its scale because this is plastic. I'm limited by my mechanical properties here. It's also the reason why these edges are thick is to help support the crank because plastic just sucks in general. But yeah, that's the steam engine. I will be releasing the files to everyone, to anyone who cares. It is a public document, so if you want to come say hi or just search it up, you can. So there you go. Have fun, I guess.